Section: Introduction. In this section, we have discussed the importance of ensuring the trustworthiness of large language models, LLMs, due to their widespread use in various fields. We highlighted the issue of hallucinations in LLMs, where they generate non-factual or arbitrary content, which can be harmful in critical scenarios. To address this challenge, we explored the idea of detecting hallucinations by sampling multiple responses from the model and checking if they convey the same meaning. This method leverages the model's uncertainty to identify hallucinations. We introduced the concept of semantic entropy, SE, to estimate uncertainty in the semantic space of model generations. While SE is effective, it requires multiple model generations for each input query, making it computationally expensive. To overcome this limitation, we proposed semantic entropy probes, SEPs, which are linear probes trained on the hidden states of LLMs to capture semantic uncertainty cost-effectively. SEPs combine the benefits of probing and sampling-based hallucination detection methods. They are easy to train, inexpensive to deploy, and can predict semantic uncertainty without relying on labeled accuracy data. Our experiments showed that SEPs are reliable in detecting hallucinations and outperform probes trained directly for accuracy. This approach sets a new standard for cost-efficient hallucination detection in LLMs. Furthermore, our findings suggest that the hidden states of LLMs inherently capture semantic uncertainty, even before generating any tokens. Through ablation studies, we demonstrated the effectiveness of SEPs across different models, tasks, layers, and token positions. Overall, our contributions include proposing SEPs for semantic entropy estimation, showing their effectiveness in predicting hallucinations, and establishing a new state-of-the-art for cost-efficient hallucination detection in LLMs. Section Summary. In this section, we delve into the challenges posed by hallucinations in large language models, LLMs, and the importance of ensuring their outputs can be trusted, especially in critical domains like medicine and journalism. We explore the concept of hallucinations in LLMs, where they generate non-factual content, and discuss the need for reliable detection methods to mitigate potential harm. Our proposed solution, semantic entropy probes, SEPs, leverages hidden states of LLMs to capture semantic uncertainty, offering a cost-effective and efficient approach for detecting hallucinations without the need for multiple model generations. Section: Related work. In this section, we will discuss previous research on hallucinations in language models, LLMs. Early studies focused on hallucinations in summarization tasks where models generated inaccurate content. Researchers also found that LLMs could store and recall factual knowledge, leading to the closed book setting where LLMs are tested without extra context. Detecting hallucinations in LLMs for natural language tasks has been a major area of study, with two main approaches: sampling-based and retrieval-based methods. Sampling-based approaches involve generating multiple completions for a query and measuring the differences in meaning between them. One method we focus on in this paper uses semantic entropy to guide our hidden state probes. Another approach involves asking follow-up questions to uncover inconsistencies in model responses. Recent work has also looked at detecting hallucinations in longer text passages by breaking them down into individual facts or sentences. Retrieval-based methods rely on external knowledge sources, like web searches, to verify the accuracy of model responses. While these methods can correct errors, they can be costly and slow. Combining retrieval-based and uncertainty-based approaches can be effective, especially in reasoning tasks where LLMs may produce inaccurate results. Various strategies aim to reduce hallucinations in LLM outputs. These include adjusting sampling methods, optimizing for factual accuracy, and fine-tuning models to align uncertainties with accuracy. Recent studies show that manipulating hidden states can alter model behavior and reveal inconsistencies. Hidden state probes are useful for understanding how LLMs process information. Semantic entropy is crucial for training our hidden state probes. It measures uncertainty in natural language generation tasks by grouping similar meanings together. We use semantic clustering to determine if two generations convey the same meaning. The semantic entropy is calculated by aggregating uncertainties within each cluster. In practice, we estimate semantic entropy using a discrete variant that does not require token probabilities, making it compatible with different models. Section Summary. In this section, we summarize the related work on hallucinations in large language models, LLMs. Early studies highlighted issues where LLMs generated inaccurate content in summarization tasks, leading to the emergence of methods to detect and mitigate hallucinations. Sampling-based and retrieval-based approaches have been proposed to identify hallucinations, with recent focus on using semantic entropy to supervise hidden state probes for better generalization performance. Section: Semantic Entropy Probes. In this section, we introduce a new method called semantic entropy probes, SEPs, to efficiently and reliably measure uncertainty in large language models, LLMs. SEPs are linear probes trained on the hidden states of LLMs to capture semantic entropy. Unlike other methods that require sampling multiple responses from the model, SEPs work on the hidden states of a single model generation, saving computational resources during testing. We believe SEPs are more beneficial than probes trained to predict model accuracy directly because semantic entropy is an inherent property of the model and should be easier to extract from hidden states. To train SEPs, we use linear logistic regression models on the hidden states of LLMs to predict semantic entropy. We create pairs of hidden state, semantic entropy for input queries, where the hidden state represents the model's state at a specific token position and layer, and semantic entropy quantifies uncertainty. We convert the continuous semantic entropy scores into binary labels to train a logistic regression classifier for binary classification. This conversion helps us compare the performance of SEPs and accuracy probes more easily. During testing, SEPs predict the likelihood of high semantic entropy in a model's response to a given input query. We analyze hidden states across all layers of the LLM to determine which layers best capture semantic entropy. We explore two token positions: the last token of the input before generating the response, TBG, and the last token of the model's response, SLT. The TBG setup allows us to assess semantic uncertainty before generating a response in a single pass, potentially reducing the computational cost compared to sampling-based methods. This quick assessment can be valuable in determining a model's certainty in answering a specific query. Section Summary. In this section, we introduce semantic entropy probes, SEPs, as a cost-efficient method for uncertainty quantification in large language models, LLMs. SEPs are linear probes trained on hidden states of LLMs to capture semantic entropy without the need for sampling multiple responses at test time, significantly reducing computational overhead. By converting semantic entropy scores into binary labels, SEPs can predict the probability of high semantic entropy in model generations, offering a practical solution for semantic uncertainty estimation. Section: Experiment Setup. In this section, we explore and assess semantic entropy probes, SEPs, across various models and datasets. We start by demonstrating our ability to predict semantic entropy accurately from the hidden states of language models, LLMs. We then investigate how SEP predictions differ across different tasks, models, token indices, and layers. Additionally, we show that SEPs are a cost-effective and dependable method for detecting hallucinations, which performs better on new tasks compared to accuracy probes, although not as well as more expensive sampling-based methods in our experiments. We evaluate SEPs on 4 datasets: Trivia QA, Squad, Bio ASQ, and NQ Open. We create training sets for SEPs using the input queries of these datasets and assess the performance on validation test sets. We consider both short-form and long-form settings, where short-form answers are generated concisely, and long-form answers are more detailed, resulting in a 6-fold increase in generated tokens. We evaluate model accuracy using the Squad F1 score for short-form answers and compare model responses to ground truth labels for long-form answers using GPT-4. We assess SEPs on 5 different models for short-form answers and use GPT 3.5 for long-form answers. We compare SEPs against various baselines such as ground truth semantic entropy, accuracy probes, naive entropy, log likelihood, and the p-true method. We use logistic regression for both SEPs and accuracy probes and evaluate their performance in capturing semantic entropy and predicting model hallucinations using the area under the receiver operating characteristic curve, AUROC. Our investigation focuses on whether LLM hidden states encode semantic entropy. We find that SEPs consistently capture semantic entropy across different models and tasks, with higher AUROC values in later layers of the model. Surprisingly, SEPs can predict semantic entropy even before generating the output, providing cost savings and the ability to assess uncertainty before generating new tokens. In the long-form generation setting, SEPs effectively capture semantic entropy for Llama 2 to 70B and Llama 3 to 70B models. We observe that AUROC values peak for intermediate layers in this scenario, as hidden states closer to the final layer focus more on predicting the next token rather than overall semantic uncertainty. To confirm that SEPs capture semantic entropy accurately, we conduct a counterfactual intervention experiment for Llama 2 to 7B on Trivia QA. By adding context to the input questions, we observe a shift in the distribution of predicted probabilities for high semantic entropy, indicating that SEPs indeed capture semantic entropy rather than relying on spurious correlations. Section Summary. In this section, we explore and assess semantic entropy probes, SEPs, by examining their ability to predict semantic entropy from the hidden states of language models, LLMs, and their effectiveness in detecting hallucinations. We evaluate SEPs across various tasks, models, and layers, demonstrating their reliability in capturing semantic entropy and their potential to predict uncertainty before generating output. Additionally, we investigate SEPs in both short and long-form generation settings, showcasing their capability to capture semantic uncertainty even in longer responses and confirming their effectiveness through counterfactual intervention experiments. Section. SEPs are cheap and reliable hallucination detectors. In this section, we explore the use of SEPs to predict hallucinations, comparing them to accuracy probes and other baselines. We also test probes in a challenging generalization setting, where they are evaluated on tasks they were not trained for. This realistic setup is different from evaluating probes in distribution because inputs in real scenarios may not exactly match the training data. The generalization setting does not impact semantic entropy, naive entropy, or log likelihood, as they do not depend on training data. Although p-true relies on a few samples for prompt construction, its performance is usually not affected by the task origin of the prompt data. We show the performance of SEPs and accuracy probes in both distribution and generalization settings across different layers for Llama 2 to 7B in a short-form generation scenario trained on the SLT. In distribution, accuracy probes generally perform better than SEPs across most layers and tasks, except for NQOpen. When comparing the average difference in AUROC between SEPs and accuracy probes for predicting model hallucinations on distribution data, we find that they perform similarly across models. The performance of SEPs is notable as they are trained without ground truth answers or accuracy labels yet can capture truthfulness effectively. However, SEPs demonstrate their strength in probe generalization to new tasks. When evaluated in a leave-one-out manner, SEPs consistently outperform accuracy probes for short-form generations in the generalization setting across various layers and tasks, especially for bio-ASQ. They show better generalization to unseen tasks than accuracy probes. Results for more models also confirm that SEPs generalize better than accuracy probes to novel tasks. We also compare SEPs to other methods like sampling-based semantic entropy, naive entropy, and p-true. While SEPs may not match the performance of these methods, it is important to note the significantly higher cost incurred by these baselines, requiring 10 additional model generations, whereas SEPs and accuracy probes operate on single generations. In evaluations for long-form generations, SEPs outperform accuracy probes for Llama 2 to 70B and Llama 3 to 70B in the generalization setting. Our results indicate that SEPs are the most cost-effective choice for uncertainty quantification in LLMs, especially when the distribution of the query data is unknown.